Welcome, everybody, to
Hello.
Aftermath Tutoring with Kip Quilter and Jaden.
Yours truly, Jaden Brewer.
Wow.
Hey, Kip, one thing first.
Yeah.
Cool hoodie there, man.
Thanks, man. Look,
Yeah.
it's got a unicorn on it. I don't know if the people at home can see, but yeah, it's definitely there, and it's definitely cool. I just want to make sure that we are actually live. If anyone out there is watching, please comment and let us know to make sure that we are doing things right. Okay, I think we're good. If you have any issues, please, if you can't hear us or something, just please let us know. Just to make sure that everything is going great. All right, so for all you guys that are tuning in and watching, tonight we have some review questions to go over. And please go ahead and the box mountain says, yes, we are live. I'm not sure who that is, but thank you for tuning in.
The box mountain.
The box mountain. Yeah, I don't know who that is, but thank you for letting us know that we are live. Okay, so last week, Jaden, we talked about a lot of different stuff, limits and derivatives and acceleration and all sorts of different things, right?
Right.
And so this week, we're going to kind of do the inverse of that, but first we need to review what a derivative is. So, what is a derivative? Is it the instantaneous slope, the tangent of a curve, a small rise over run, all of the above, or none of the above? I'd love it if you guys would go ahead and comment away and tell us which one of those you believe is correct.
And while we have this little time delay, Kip and I are going to make small chat, aren't we?
Jaden, apparently there's something wrong with my mic.
Something's wrong with your mic?
It's choppy now.
Uh-oh.
Your voice is also choppy. We'll see if that helps at all. Please let us know if it continues. Thank you for letting me know. Okay, we got, never mind, half and half. Hold on,
yeah.
We'll see if this does anything.
Can you hear me, Kip?
Uh-oh, Jaden, we're in trouble.
I think it might be your headphones, Kip.
All right, Jaden, I'm gonna have to go ahead and do something really quickly. Please, sorry for this quick issue, but we're gonna go ahead and switch this to that, switch this to that. Jaden, can you speak, please?
Hello, can you hear me?
I can hear you. Anyone else out there?
I think it's a lot better. You were a little choppy with me too, but now you're not.
My headphones were dead, so I switched over just to my standard microphone on my laptop, so now there's going to be a little bit of humming in the background, but everything should be way better. And we'll just have to deal with that for now, and maybe my headphones will charge and we'll be able to switch back. So sorry about that, guys. Okay, so now, what is a derivative? If you guys want to go ahead and comment, and Jane and I will keep on plugging along here.
Yes.
And if no one's going to answer, Jaden, what do you think the answer is?
Well, I remember last time hearing about instantaneous slope, so I'm gonna say it's A.
That's good. I agree with you. But Jaden, quick, when we take a test, it's good to read all of them, right?
Oh, I should have
Because
just stopped right when I
no,
hear a good.
we got
Oh,
D, yo. That,
E. Yes. Good job.
that, good job. Yeah. So it's also the tangent line of a curve and a small rise over run. Okay.
Awesome.
All right. Moving on to review question number 2. What is the second derivative of x squared? Jane, let's hop on over to where we can write. And I'm on the wrong slide over here, but
So if we remember from the very end of last week's lesson, we were doing the power rule for derivatives. And that's the the easy way to do these. Kip, you want to do the first derivative and I'll do the second derivative, or should we let them write it out in the comments?
why don't we talk a little bit about the power rule and let them try to figure it out in the comments while we just kind of go through it ourselves.
Okay.
So Jaden, if we've got the power rule is like this, we've got x to the n, right? And if we want to take the derivative, then we get x or nx to the n minus 1, right?
Right.
Cool. So, do you want to do the first derivative because no one's commenting?
Sure. Dx of x squared equals 2x. And when you have a number right next to a variable, that is multiplying, just to clarify if anyone didn't know that.
Yeah. We've got a question asking what even is a second derivative in the real world. I'm not.
Acceleration.
Yeah, acceleration. If we're talking about displacement, that's the only one that I can think of right now.
Off the top of our heads.
Yeah.
Well,
it's the second.
we get a lot of second derivatives as just like zero for linear equations.
Yeah. I mean, they can be used as well to figure out if something is increasing or decreasing at a certain point.
But yeah, acceleration is probably the best one that we can think of off the top of our heads.
Okay.
Good question, though.
Yeah, great question. Also, guys, just for kicks and giggles tonight, I'm willing to Venmo the person that comments the most 50 cents. Okay?
Ooh,
So get commenting away, but
that's
also
like
pay attention at the same time.
Yeah, that's like 2 quarters, Kip, or 50 pennies.
Uh-oh, Jaden's got a little echo going on. I was worried about that. There. I'm not going to hear you like at all now, but hopefully that helps.
You're not going to be able to hear me?
No, I hear you, just not great.
Okay.
Okay. We just have to hold on long enough for my headphones to charge up a bit. So, all right. So now from there, Jaden, let's take the second derivative, and we get. So if we do that again, right?
So
So
you
just
take
to
1.
clarify what you did here, we had x to the second, so you did -1, and you multiplied it by the 2, right? So that's how you got that. And then we go again and we do 2x times 1, and then you do 1 minus 1, and so you get 2x to the 0. And Jaden, what's anything to the 0?
1. I think I echoed.
Uh-oh. Hold on just a little longer, people. Just 5 more minutes of echo. Alright, so we get 2 equals the second derivative, right? And that was a review of the power rule and the whatever else I just said. Yeah, we got power rule. Okay.
Okay, before we move on, do you think we should do a polynomial with more than one term?
Sure, Jaden. Go ahead.
Okay, so what if instead we had like x cubed plus x squared? Right, how do you take a derivative with 2 terms?
If there are 2 terms like that, then can't we just do the power rule individually to each one of them?
Yes, we can.
So
So
you do it.
you want
I
to
want you
show
to
them?
do it.
Okay, I'll do it. Okay, so we take the first derivative, that would be 3x squared plus 2x. And then if we were to take the second derivative, we'd do a 6x plus 2. And why do we get the 6? Because a 2 times 3 equals a 6. So we just did the derivative individually with each term. I didn't show all the little steps in there, but I think everyone's smart enough to follow along. What do you
I think
think,
you're
Kip?
right. I think we did good. So
And would this work if you had any number of terms, Kip?
yes, it would work no matter how many terms we had.
Okay, awesome. All right, so we move on to the next slide, area.
Yeah.
Okay.
All right. Moving on to slide number 3 here. Okay, Jaden, do you want to talk to us a little bit about what area is?
Yeah, so most people should probably know what area is, but this is an important thing to refresh our memories of for tonight because we are going to be talking about integrals. But anyways, an area is the amount of space something takes up, right? It's generally in 2 dimensions. Surface area would be your 3-dimensional shapes, but today we're just talking about area. And yeah, it's just a space basically bounded by a shape. Lots of times you can find area in like squares or rectangles by doing the length times the width, or in a triangle you could do the base times the height times 1/2. So those are just a couple simple shapes that we know the area of. But what happens when we don't know the formula for like a shape? What if it's some crazy curve that would seem impossible to find the area of? That leads us to a big topic for tonight, and that is integration or integrals. Okay. Is that good enough for the area, Kip?
Yeah, Jaden. Sorry, I'm just trying to get my headphones set back up here so we can get rid of all this stuff.
Okay, I'm gonna move on.
Let me know if I'm choppy again, everyone. But I hope to be less choppy now and not hearing echo. Might have been. Okay. Yes, everything should be good now, I think. Okay.
Yeah, you sound.
We got a question. What about 3x cubed x? That's for another day. We haven't gotten that far.
That's a little bit more complicated of a derivative. Yeah, so we're just talking about the area, and I was explaining what happens when we get to shapes that are no longer these simple squares, triangles, trapezoids, all those. What if there's some crazy curves, right? And that leads us to integration. And are we on that slide?
We are now.
Okay, awesome. Okay, so an integral is the area under a curve. All right, so we have this crazy curve, trying to figure out the area under it. How do we do that? We have to do, so you can like approximate it by taking like rectangles of this area, but it's going to be a little off because your rectangles will go above the curve. But then we can make the rectangles skinnier and skinnier and skinnier until they're an infinite amount, and they basically line up perfectly with the curve. But how the heck do we do that, Kip? Right? That just seems impossible.
Yeah. So let's go over to our Jamboard, Jaden, and kind of draw it out a little bit.
Okay.
So if we go and look at this picture, yeah, sorry, I've been trying to fix audio issues, so I haven't been paying a ton of attention. But this is going to get much better from here on out, I promise, guys. It's going to be a lovely rest of the night. So Jaden, on this graph on the right here, right, the integral is essentially the area under the curve, or an inverse of a derivative. So we've talked a little bit about inverses before, but it's essentially doing the opposite, right?
Okay.
And so like you were saying, I think, is we can go ahead and make these rectangles under a curve, right? So on our picture over here, we have these areas. And we can go ahead and sum up all those different areas together to get this area under the curve, right? And so what happens is we can go ahead and we can keep breaking those up, I think, like you said, into smaller and smaller chunks, right? We could go ahead and make smaller.
Dude, are you holding shift, dude?
What?
You gonna hold shift?
Dude, I'm holding shift. Look at me go. Boop.
Dude, look at those straight lines, man.
Dude, look at those straight lines.
So we're breaking it up smaller and smaller. Boo, 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 boo. Whoa, we just did the same line.
Whoa. And so we could keep doing that over and over, right? So now we've got this
Right.
area and here, and this area and here, this area and here, and we can go
So
ahead and keep making those smaller and smaller.
the
Um,
more individual rectangles that we draw, the more accurate this area is going to be.
right. Because as you can see here, right, we could either over approximate and go up above, or you
Uh-huh.
could under approximate and go below. Um, and so as you get closer and closer, though, each one of these lines is going to line up directly with a certain part on the graph, right? So
Right.
that's where this really long, lovely equation comes from here. That probably looks pretty scary for a lot of people out there watching. Um,
I think we should break that down a little bit. What do you think?
I think we should, Jaden.
Yeah. So first, the limit, right? We talked about limits last week where you take this piece of whatever you want and you get closer and closer to a certain value you want, right? So that's kind of what the limit is saying, where we're making these rectangles and we're getting them smaller and smaller to a different area we want, right?
Right.
Okay. And then this weird sideways M, that is a summation, which means we take a whole bunch of different parts and we're just adding them together. Okay. And then the f of x sub I times the delta x, right? Right here and right here. So those things are your length times your width of these rectangles. Okay,
Jaden, that
that's
sounds like a lot like area to me.
yeah, exactly, Kev. I'm so glad you said that. That's wonderful.
Yeah.
That's all it is. Is taking all these rectangles, multiplying their length times their width, and just adding them all together. And that is how we get the full area under this curve. Does that
Okay.
make sense?
Yeah, I think I'm getting some. I'm starting to make sense. Yeah, it's getting clearer and clearer. So then let's. So what you're saying is we're essentially going to add together all these little areas, right? Where the change in x along the x-axis, right? That's going to be
Uh-huh.
our width, and then the height at that certain point will be our um, length, right?
Right.
Okay. So Jaden, what happens when we get to the right side of that equal sign? That looks, I don't know. I mean, it's a lot more stuff going on. So what's
So
going
the
on?
right side of that equal sign, if we notice, we keep that limit there because
Okay.
that's important because we're getting smaller and smaller till we are approaching infinity, right? Because we're going to want an infinite amount of rectangles. But all this does is show that we're adding each term, right? This is term one, term two, term three, and so on and so forth, right? That's just doing that summation part, right? It's just taking that M symbol and actually writing out each individual addition.
Okay.
So the summation part just makes it a little neater so we don't have to write all these terms out. Uh, yeah, I think that's a good way to explain it.
Yeah.
Anything you want to add about that, Kip?
No. Yeah. I think that you did a good job there. And then lastly, right, this very bottom part here says where the change in x is just going to be, if we're looking on a graph, right, we have x sub I, so it's just going to be that um, x sub I minus x sub I minus 1, right? So if we have,
So that
if
would be
we,
like x2 minus x1,
right, and if
right?
we look on the
Or
graph
x,
here, that's this line over, right? That's this distance right here.
right,
And then the key is, right, is so if we have an n number of these boxes, right, as we get that closer and closer to infinity, then these boxes get smaller and smaller and smaller.
yep.
So we're going to go ahead and move on to the next slide. We'll stay in the Jamboard for it. Oh, wait, we got graphs here if we want to play around with graphs. Do we want to play around with any graphs?
I don't think not yet, but I
Okay.
think we probably will want to, but
Yeah,
maybe not
not
right
yet.
now.
Okay, well, let's go back to the actual slides then. So,
So
Jaden,
all
what
of that
the...
from the previous slide
Uh-huh.
is equal to this, right? This big equation right here, this is just the integral from a to b of f of x dx, right? So this is just saying I want to find the area under this function from a to b, okay? And this is just a lot neater way to write everything we just wrote on that previous slide, and it's also underneath it. And this is just a notation that we use, and it was from Leibniz, I believe. And he was basically like, hey, I'm going to write this long S because I would rather write this long S instead of the summation symbol.
Yeah. And
And
what about what's that d of x, or dx? What does that mean?
that that's the basically the change in X part.
Okay.
Right. That's what I think it is.
Yeah.
Is that what
I think you're right. But I like it's once that n gets to infinity, right? So it's that infinitesimally
right,
small change in x. Um,
right.
and so that integral essentially just becomes a really fancy shorthand way to write that big, nasty, long thing that we have written out.
Right.
And in particularly in this next little chunk down here, right here, where we have where we take the limit again, but this time we're going to say that each one of these rectangles is broken up into the same number or it's the same length, right? So we have this a minus b divided by n, which is the number of rectangles we're going to have. And so as we have more rectangles, right, that change in x is going to get smaller and smaller and smaller. And as it goes to infinity, that means um, our changes are going to get closer and closer to 0. Okay?
Yeah.
And then that b minus a, or that a and the b, just simply mean kind of the area in which we're going to be looking, right?
Right.
Okay. Anyone have
Should
any
we
questions so far about what we're doing? If you do, please let us know.
should we hop on over to the Jamboard and do an indefinite integral?
Sure. I got some graph paper up on page 4.
Okay. So on that slide that we were just on, that was a definite integral. A definite integral meaning that we would give you an answer to the question, right? We would give you an actual area. But what if we don't have these bounds A and B? Then it'd be called an indefinite integral. So you would give a function plus this constant that we will talk about. Okay. So that will look We have an integral from of f of x dx equals, well, that would equal, what? Hold up, what does that equal, Kip? Uh, okay, yeah. Plus c. Okay, so that c, that is, we're pretty much saying uh, this integral represents this family of functions, right? So this function plus a constant, it could be changed to pretty much anything you want, right? Uh, the definite integral, that's where we get these like specific sections of the function, whereas this one, it can be anywhere on the function, or it can be like anything that like closely relates to that function. If you add like just a constant to something, it can either lower it or raise it, right? It can shift it right or left. So all of these different functions are being represented by this fx plus c, if that makes sense. And then we'll also explain it in the physics way, where Pip will explain that. And that one might make a little bit more sense than what I just said.
Yeah. So I think, it's just important to, if we draw it out really quickly here on a graph, um,
Yeah.
if, we've got, look at that straight line, dude. Straight as can be. Um, so if we have some
So maybe.
function and it's like going woo, 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 like that, um, an indefinite integral, right? We don't have any bounds on this. But if it was definite, then we'd say from like point A to say point B, right? Um, but if it's indefinite, we care about it across the entire spectrum of the whole function,
Yeah,
essentially.
and it could also be, here, I'll draw another one. Wow, look at those straight lines.
Dude, that was so straight.
Holy moly. It could also be, let's say our function happened to be like just x. So it'd be this straight line, just kind of diagonal up like this. But then the plus c means it could be shifted up here or down here, right? We'd have all these different possible functions from it.
Right.
And that's what I meant by like function, like this family of functions. It could be shifted all these different ways.
Okay. So yeah, it can be shifted all these different ways. So now, what is the point of this, right? Why on earth have we taught you guys these antiderivatives, these integrals? What on earth? How does this benefit us? Who cares? Well, I'm a physicist. I like physics. Um, so we're going to go ahead and jump into something that's really important with physics now to kind of help you guys understand and see how we can use these. Um, so, we're going to start learning about one of the big main things we learn about in physics at the very beginning, in mechanical physics at least, which is something called the kinematic equations. Um,
Ooh,
they're used to
kinematic skip.
yeah. So kinematics just kind of means essentially Um, kinematics really just means that it's, movement of some sort, right? Um, and normally we use these when there's a constant acceleration. So if we don't have a change in acceleration, but rather a constant acceleration, kinematics can be an amazing, amazing tool. Um, One of the main things, if you neglect air resistance, so say you're on the moon, you can really easily use this to calculate projectiles because there's a constant acceleration due to gravity. But
Yep.
we can use it to predict some aspect of motion, right? Um, and there's going to be four main equations that we're going to go through tonight, and we're going to actually derive all of them ourselves, okay? And
Whoa.
then the next thing is that these, equations are kind of essentially all the same thing, but we solve them differently so that we can get rid of certain aspects, certain variables that we may not know when we know other ones. Um, and the most important part is we can actually find these equations using calculus and using this idea of, you know, the integrals, all right? And so for the next little bit here, we're actually going to be using some real world examples here to show you guys kind of how powerful of a tool this stuff can be. Um,
Ooh.
so let's hop on over and start solving some equations here, all right? So this first equation that we've got in front of us says V equals VI plus AT. Well, what on earth does that actually mean? Um, so what that means is that we're going to take a velocity at a given point, okay? And we're going to say that is equal to the initial velocity plus the acceleration times time.
Oh, I thought it was just you add the letters together to spell a word like Viat. Is that what it is?
Yeah, Viat. It's like, it's Fiat's cousin. And
Yeah.
Fiats are cars, so they have acceleration. Um,
Right.
yeah, so let's see if we can derive these things, all right? So I'm going to start with acceleration, and I'm just going to write an A here, okay? And if you remember from last week, Jaden, your head turned sideways.
Yeah, I don't know what's going on.
Oh, look, there you are. You're back. Um,
Woo!
so let's say that our A is acceleration, okay? Jaden, do you remember
I thought a
um,
head tilt. That's
what the derivative of velocity is?
that would be acceleration.
Okay, so if an integral is the inverse of a derivative, what should be the integral of acceleration?
Then it should be velocity.
Okay, and this is all with respect to t, right? So we could do a,
Okay.
um, so it's a constant acceleration, so we just simply have a, right? And we could make a graph over here and go boop, boop. Look at that straight line.
Whoa.
And so we'll just say that this is a at this point here, okay?
Okay.
And it's constant, so it's just a horizontal line. And this is t down here. And the integral is just finding the area, right? So if
Okay.
we didn't have this bounded, let's just say we wanted to find the velocity at this point here on the graph, right? That would be the area right here, right? So
Okay.
according to that, we could just do a times t equals v. Now, Jaden, that looks awfully close to what we
Right.
have over here, right? But there's something missing.
Yeah, we're missing that VI, the initial
That
velocity.
the initial velocity. Um, and so, if we actually wrote this out, we could say that v equals the integral of a dt. Okay.
Okay.
And so when we take an indefinite integral, right, there's always going to be that plus c at the end. Okay.
Right.
So we get v equals at, which we found, right? And we can use the power rule to do that. It's the inverse of the power rule for derivatives.
Right.
So if it's going to be a divided by n and then n plus 1, right? Because if we remember, the inverse of that is n minus 1 times n. Or wait,
Right.
is that right? Or is it n?
Yeah.
Yeah, that's right. So
Yep.
then we get
But it would be on the variable, not on the A.
you're right. Okay, thanks. So in this case, it
Yeah.
would be t, right? Um, but our t in this case is 1 to start out with, right? And so we just would have 1 to the n. I don't know how you actually start this off like this. I guess this is t, yeah, but our n is
Yeah.
0. Okay, n is 0. There we go. That's what I'm saying. So you get t to the 1 over, no, see, this has got to be n plus 1 down here too.
Uh,
Because you have
yeah.
0 plus 1. Okay. And so we get this, we get a t plus c equals v. Okay? And this is technically a v of t, right? Because v is a function of t.
Right.
Um,
That's looking awfully close.
we're getting there, right? But we've got this c. Um, and we know that it needs to equal the initial velocity, all right? So what we're going to do is we're going to say that what, we're going to say that v of 0, okay? So at time 0, we're going to say that equals vi, okay? And we're going to say that that equals a times 0, right? Because it's v of 0 plus c, and we get left with vi
VI
equals
equals
c.
C.
So then you get
Whoa.
at plus vi equals v. And that is totally solved. And I would even go ahead and say that's mathematical. Okay?
That is really cool.
And so here's why that
So
vi.
let me, real
What?
quick, Kip.
Yeah.
Uh, so T represents time, right?
Right.
And when you plugged in V of 0, you're just saying at time 0, I'm going to define this as my initial velocity,
Right.
right? Okay, just clearing it up for everyone out there.
Thank you. I appreciate that. Yeah, so
Yeah.
I'm saying at time 0, when we first start looking at this, right, we're going to call that our initial velocity. Okay? And so this kind of shows how the c matters, right? If we go back to that last slide that Jaden was drawing all these lines, right, this starting point right here could be our VI if this was a velocity versus time graph, right? Any one of these points could have been our VI, but we actually solved for it to show which one it actually
Right.
was. Okay, Jaden. Moving on to equation number 2. We've learned 1 out of the 4. Okay, so we need to find the second one.
Wait, this looks
And
like we're gonna go from velocity to displacement.
yeah, so if we remember from last week, the derivative of displacement was velocity. So
Yep.
if we want to get to displacement, we can take the integral of the velocity. So we can say that d
Cool.
equals the integral of v of t dt, right? And
Right.
so we can go ahead and say that d equals, and so now we've got this though. We've got the integral of a of at plus vi, and these are all dt, or multiplied by dt.
Right.
And like with the power rule for derivatives, we can break this into two different integrals. So we can go ahead and say that d equals the integral of at dt plus the integral of vi dt. Jaden, do you want to do those integrals for us?
Yeah. So from the first one, we will get 1/2 at squared plus c. And then from the second one, so this will still be a plus, we will get the I d plus c. I guess we could say c1 and c2, right? Just so we have them differentiated.
Right. Okay. And now, Jen, just really quickly, right? How you got those integrals is you had t to the first, so you
Added
added
1,
one and then
yeah,
divided by one.
by that new exponent.
Yeah. And same thing with the second one, right? You had t to the 0, so you added one and then
Yep,
divided by that new exponent.
yeah.
Cool. Um, so in math, if you have two constants, you can combine them to make one big constant, right?
Yeah, I love constants like that.
Me too. Maybe we should go to another slide. Um,
Agreed.
and I'll just add one in here real quick for all of you viewers. Do.
While he's making that new slide, if you haven't already, will you leave us a like and subscribe if you haven't? If you are actually liking the content and want to subscribe,
No,
but
I think you
yeah,
should no matter what.
yeah,
Um, sorry, I didn't. I thought we'd have enough room here, so my bad. Okay.
good.
All right. So we had so if we added our two c's together, we get to 1/2 at squared plus vi t plus c. Now, Jaden, that looks awfully close to this, right?
Right, but now we just have a
We have this
con.
pesky little c there. Um,
Right.
so with displacement, we can go ahead and pick any point really to be 0, right? And
Okay.
so in this case, we're going to say, and this is going to be d of t again, we're going to go ahead and say at time 0, our displacement is going to equal 0, all right? So we're going to have 1/2 a 0 squared plus vi 0 plus c
C
equals 0.
equal.
And all of these are going to equal 0. So we get c equals 0, because anything multiplied by 0 is always 0. And
Right. So
now we
then
have
we don't
gone
even need
ahead
to write
and
sign.
solved that equation, right? Answer is
That's
mathematics.
awesome.
Okay.
Woo!
Woo! All right. So, guys, I think we are done with really the calculus portion of tonight, but we still have two more equations to go through. And like I said, these equations, oh wait, so you use the integrals if you know the velocity of a spaceship but don't know the displacement. Yeah, okay, so these are good. That's a really good question. Um, so yes, when it comes to doing things, a lot of times what you'll actually know is the acceleration of an object, right? And if it has a constant acceleration, finding the acceleration is really easy, and we'll see that on the next slide. But essentially, it's just going to be you can take any increment of time and have your velocity. You essentially find the average between 2 points in time, and that finds your acceleration. And if you know acceleration, then you can actually go ahead and solve a whole bunch of different things, right? So in that first kinematic equation that we solved, we can actually now find a velocity at any given time, right? And now that we found the velocity, we can actually go ahead and find the displacement at any given time. And so that the thing about the integrals and the calculus that we've done, right? This is for a constant situation where nothing's changing. And these are, when you're getting into introductory physics, that's kind of the only thing you deal with. But you could actually use these integral equations. You could use the integral, say, if you had a non-constant acceleration as well. If you had a function for your acceleration, you could find the integral to find the velocity, and then you could take the second integral to find the displacement. But for the kinematic equations, people have already done the work for you, so you don't actually have to take an integral, right? But we're using this as an example to show how integrals are done. But most of the time, most physics students, when they see these equations, they have no idea what an integral even is, and they're just given these equations and say, here you go, have them. But I feel like it's much more important to show where they came from and why they exist. So there's a little spiel on that. Okay. By the way, remember, guys, you get 50 cents for the most amount of comments. So I think there may be a tie between the Box Mountain and Kelsey. So if anyone else wants their 50 cents, comment away. Okay. So moving on to this next equation. What we're going to do is we're going to take that other equation, Jaden, where it said the velocity is equal to VI plus, what was that? Sorry, plus AT. Okay?
Yeah.
And now, what we are going to do is, like I said, we can use these different equations depending on which unknowns we know and what we don't know. So let's say we know a velocity at a certain point, and this is what the second equation says, is that let's say we know an equation at a certain point, but we don't know its acceleration, okay? So what we can go ahead and do is we can rearrange this velocity equation to solve for A. And we get V minus VI divided by T equals A. Okay? And it makes sense if this is a constant acceleration, right? Because if you have a graph here, look at these straight lines. Straight lines for days. Oh gosh, that one wasn't that great. Straight lines for days. over here.
So straight. That's
And if you
amazing.
remember, we have this slope, right? If we say that VI is here, and then we say that V is right here, and this is T down here, then it makes sense, right? Our rise over our run is going to equal A.
Okay.
And then from there, we can plug it into our displacement equation, which we know already, which is this D equals VI T plus AT squared. And if we plug this into A,
Plug that into A. Whoa.
what do we get? We get D equals VIT plus 1/2 in parentheses V minus VI over T squared, and then we can go ahead and cancel one of those T's with that T down there. And so then you get D equals VIT plus 1/2, and we're going to put the 1/2 as just over a 2, right? So we've got V minus VI over 2 times T, okay?
Okay.
And then from there, we can we got a comment saying, give me something I can relate chemistry with. Orbitals. Oh boy, that's way, we'd have to get into some quantum physics, and anyways, it'd be it'd be rough.
Yeah.
Okay.
Orbitals.
So we can pull out this T from both of these, right? And we get D equals VI, or sorry, we'll put this T out front here. Or well, no, we'll put it behind. So then you get VI in parentheses plus V minus VI over 2. And then we get this T, right? And then you can multiply this by 2 to get it to a fraction, because, you know, when adding fractions, you have to have the same denominator. So you get D equals VI 2VI over 2 plus V minus VI over 2. And then you can add these together. And sorry, there's a T out front here. And this equals VI or V plus VI over 2 T. And that is now solved. Okay? Alright, we got 2 minutes to do this last one, and this last one's a little bit more of a doozy. Let's see if I can remember how to do it. Okay. Jaden, let's think here.
Yeah. We can use any of the equations that we've already used, right?
Right. So in this, okay, here we go. In this next one, we don't have a T, right? So we need to make a substitution for T.
Right.
So which equation do we want to do that for is the question. Let's go ahead and say we'll solve this equation right here again, but for T this time, maybe. Is that the right way to do this? I just did this earlier today, but I can't remember where I did it. Okay. So we can go ahead and say that T is equal to V minus VI divided by A. And then we can plug that in to our equation again, which was D equals VI T plus 1/2 a, and now our t is going to be v minus vi squared. Sorry, this is like that. And so one of our a's is going to cancel. And then we're going to get v squared plus see, this is going to be nasty. I think there's an easier way to do this.
No, that would be v squared
minus
plus
2vi vvi, right?
Yeah.
Yeah, this is going to be nasty. And this is going to be plus vi squared. Oh, no, Jane, I don't want to do it this way because we also have this t over here.
Yeah, we do.
Oh, okay. That's not the right way to do this then.
We'd get the right answer.
I know, but it's going to take too long.
Try plugging in the t into the d equals the v over the 2t. That equation just above in the one we
Into
just
this
solved
one?
for. Yeah, does that do anything?
I mean, it's probably a more simple way. Yeah, that's probably way better. Yeah, so we take this equation. Thanks, Jaden. And if we take that equation and plug in for t, I'm going to erase all this. Boop.
Boop.
Sure, calculus is cute. That's not the word I would use to describe it. I'd describe it as amazing, but not cute. Okay. So this is equal to t, and we're going to plug t into that equation, so you get d equals v minus vi over 2, and we're going to times that by, in parentheses, v minus vi over
Wait,
a.
if we should have, shouldn't
What?
that be a plus here? Because isn't that what we solved for right here?
Yeah, it is. I wrote it down wrong. Thank you. That's a plus sign.
Yeah. Because that's going to make it
Yeah,
better.
okay. And so then when you multiply fractions, you do top times top. And so you do this to this, and this is called, I can't remember what it's called, but essentially what you get is you get, what?
First foil, first outer, inner, last.
Yeah, I know, but there's this kind of square is
Oh,
special,
yeah, okay, I see what you're saying.
because you just get v squared plus or minus, right, vi squared. If you guys have questions on how I'm doing this, because I'm going really fast, please tune in next week, or on actually Thursday, and we can go more in depth into this. And so then we've got 2a, and this equals,
by the way. Yep.
what?
Conjugates, I believe.
Conjugates, yeah. And so then from there you multiply this to that side, so you get 2ad, right, equals v squared minus vi squared, and then you can flip it, or you can add vi to both sides. I'm running out of room here. I'm going way over to the far right, and you get vi squared plus 2ad equals v squared, and that is now solved.
We did it. Wonderful.
And this whole lesson has been so mathematical. Thank you all for watching and participating. We really appreciate it. Anything you want to say, Jaden?
I think it's just beautiful. That's all.
If you haven't already, hit that like and subscribe. And every Thursday, guys, as well, we do live tutoring where anyone can hop on and ask us any questions from high school math all the way up through calculus, as well as anything really in physics up to kind of modern physics. Um, and so if you yourselves don't have any questions, but maybe have friends that need help, please let them know about
Yeah.
this free resource for them. Um, and thanks for watching. And we will see you on Thursday. And if not Thursday, next Tuesday when we go over a little bit more intense stuff, which we'll start probably learning more about these kinematic equations and kind of how they really work and why they're important.
Yeah.
And as well as probably go over some useful features of derivatives as well, besides what we've talked about so far. So, thanks again, guys, and good night. Peace out.
Good night.